Okay, so here are some current temperatures across the U.S. Just some scattered weather stations. Cincinnati 18 degrees right now. I'm showing 19.7 degrees. That's about 20 miles east of the city. 20 degrees in Cleveland, 20 in Chicago, 7 in Kansas City, -1 in Sioux Falls, 37 in Denver. But if you look at these temperatures, -1, 7, 18 in Dallas. That's cold for Dallas. 30 in New Orleans. There's 30. Now you got 82 in Miami. So be a nice place to be. Over here in Bermuda, 70 right now. There's a nice comfortable temperature. So if you look at this, you can pretty much see that high pressure that came through the central U.S. dropped down. This is just the Arctic air mass. -1, 7, 18, dropping all the way to the south. 33 in Albuquerque, 37 in Denver. Um, Nothing unusual in Denver, really, but Albuquerque, that's a little chilly. High pressure just pushing to the south. Well, let's pull the sea level pressure. All right, here's high pressure just pushing all the way down right through the central U.S. A low pressure system over the Four Corners. We've been seeing that quite a bit here the last several days or few weeks. Here's that low pressure system that went through, frontal system. You can see the troughing along the east coast, pushing through, wrapping around this high pressure system that would be there, and then your warm air advection coming from the south. So you probably have a warm front coming out of that low, cold front behind that low into the troughing here. A pretty well developed low pressure system. If you look at the jet, probably ridging there, going across and supporting both these systems. So let's throw some isotherms on here and let's see what we got for how these are baroclinic systems. So definitely baroclinic. The isotherms are crossing the isobars, and like I said, you can see all the thermal advection. Cold air from the north, cold front through the trough. Depending on what this high pressure system is doing, I don't think it's still building. I think it's probably weakening at this point. So I would say, bring that cold front down, go across here in this wide open area, and there's really nothing to change your wind directions or anything. So bring that to maybe like a stationary front, and then back up to this warm air advection with your warm front and coming out, meeting that stationary front, and then your cold front coming out of that low, dropping down into the trough. I mean, if you look at the cold air advection, there's really not a lot of cold air advection even in that trough. So I'll throw the computer fronts on here. They get a little messy, but we'll see what happens. I'll maybe erase this first because it likes to put in its own highs and lows. And if I leave these, it'll get pretty cluttered. But let's throw some station plots on here real quick. Look at the data, and then we can tell where our temperature breaks are and the separation of these air masses. All right, so circulation around the low, counterclockwise. See that warm moist air being pushed up. Right there, IFR conditions in the red. Snowfall, the Panhandle of Texas, up into Kansas. -39 degrees right up there at the tip of Texas. 39, then I see a 24 up in the New Mexico. There's a wind shift, pretty good wind shift right there. Here's the winds out of the northwest coming down, and then what we should see is a southeasterly or southwesterly flow from around that low. I mean, with the friction on the surface, you get some backing. So this wind here, I'm not sure exactly what's going on with that one. But if you look at your wind shift, I'd probably place that front right through there. So the warm air advection, I mean, there's warm air advection there, but you're not going to really pick it up. We got 34, 25. I mean, you can see it based on the isotherms. As far as temperature differences, those temperatures are dropped so bad, just so cold that from the high pressure that went through there that are still in that edge of that Arctic air mass. Now look at the winds. If we had to put our warm front Here's the winds blowing across. I would be blowing across that warm front, bring that warm front right out of here. I mean, that wind, like I said, it's out of place. This wind makes sense coming up. Then the wind's crossing over, so your warm front would be down in this area. Like I said, we'll throw the computer generated fronts on here in a minute and see what we got. That cold front, there's a wind from the southwest, kind of a westerly wind. So I would bring that cold front, would lay pretty much right into that trough. Look at some of those temperatures, like a 49, 47. Head of that front, 68, 71, 64. A little hard to read. It gets a little cluttered on here. There's a 37, 64. I mean, you're definitely got that cold front. You're in that cold air mass back behind that front. So, all right, let me erase this. I'll throw some isobars on there without the highs and lows, and then we can throw our isotherms and then throw some fronts on there. See what we got. All right, some isobars. There's the lines of equal pressure. These little high pressure systems is picking up like separate highs. There's really probably not 3 separate highs. There might be one station reporting a little bit higher pressure, like in Iowa, one down here. But there's, it's pretty much going to be an elongated high. Just the computer sees those one stations with 1/10 of a millibar higher, and it throws a center there. It's all about how the computer takes these lines, because if you would actually plot these lines, put every station on this map, plot these lines, you'd just be zigzagging all over the place. It would be pretty hard to read. The computer kind of averages things out and then just smooths it out. And if it has a couple laying in there that are a little bit different, then it kind of makes another high pressure system. Just gives you another center. Alright, so we got our plots. Got our pressure systems. Let's go throw the fronts on. Alright, so we do have a front coming out of that low pressure system. I'll probably move that back into that trough just a little bit. But looking at that wind speed there, that wind we have, it's only a 5-knot wind. It's on a buoy, so I kind of take them with a grain of salt too. The winds over the ocean can shift quite a bit, but being out of the northwest and then down here in Florida, being out of the southwest, there is a shift right there. So that front could just land right in that area. Then it's got a post front. Basically, this just separating this warm air from the cool air, and that cool air from the cold air. So it's got a post front and then a couple troughs back around that low pressure system. So as we see any precip develop, as the winds come out of the north with this trough pushing to the south, if we see any precip develop, we'd maybe have something along the mountain range there in northern Kentucky. You get these shortwave troughs spin around these low pressure systems as they fill, and you can get on and off showers at any time during the day from that. Rain showers, snow showers, all depends on the freezing level. So that's pretty much why you just see the snow comes and then it goes and it comes and it goes. You'll get these troughs that move through the area and just creating more snowfall, and then it'll be between troughs. You'll get a little bit of ridging that'll stop the snowfall. Then another trough comes around, and then you'll get snowfall again. So like up here in Canada, they're reporting snow in that area. But you got that warm air advection and that warm moist air off the ocean being pushed inland right there. So just the little bit of lift from the land can get that precip up just enough to condensate and then fall to the ground. But like I said, you got a post frontal trough, a post front. You got a front and then a secondary front. This front is probably off the chart, maybe not. It's bringing it down, then back up to a stationary front up into that low pressure system. So this low pressure system over the four corners, let's see, that was back in here. They'll close low. If you look at the wind direction, northwest, then a southerly flow, kind of looking for a little bit more easterly flow than that, but you're looking for that rotation to center that low pressure system. Trying to see these pressures, 1005.3, 1005.2, so you have a little bit lower pressure there. 1007.4, 1005.0. Right there's the lowest pressure that I see reported by a station, so put your low pressure system right in that area. Bring the looking for the winds. There's a wind shift. Warm air advection right across those ISO bars. You get all that warm air advection. I'd probably put more of a warm front coming down into that. Then a cold front, probably shooting a little bit more straight back. They got kind of troughing back in that area. There's a north westerly wind at 66 degrees, 64 degrees. Probably in the warm sector there. That cold air advection's in the backside. You get a 60 to a 66, 61. So a little weak cold front, maybe just some troughing back in that area. Definitely got the thermal advection. Like I said, this computer throws all these highs and lows. It just, if it sees one little area of just 1/10 of a difference, it'll try to throw a low pressure center in there. So you got to take those computer generations, with a grain of salt too. So, all right. So that is the surface chart. Let's go look at a thickness chart real quick. Go run the script on that one. I can build that at once instead of picking every item separately. This just takes not too long to just come together. The 1,000 to 500 millibar thickness is what we're building here. This is going to be what the atmosphere thickness would be from 1,000 millibars, which is about 360 feet, up to 500 millibars, which is about 18,290 feet. Just shows you the different thicknesses of the atmosphere, and the 540 line is the one that's the magical line on this chart. That purple line that comes down, sinking all the way down into Texas for that cold air. Anywhere north of that line should be snow, and it's pushes that cold air just comes south. That thing goes around the height that you would have to for any precipitation that fell into the thickness. The lower heights to the north through that cold air mass should hit the ground as snow. Anything along that line would be mixed precipitation. Anything to the south be rain. So we got, like I said, with snowfall in West Virginia. We've seen those shortwave troughs coming around. We got one up here. That's up over in Canada, just across the lake there. So there's the thickness. We're looking at that 540 line. That's the main thing on that one. And then if you look at these thickness lines, how tightly packed they are through here, that gives you a pretty good indication of where the jet stream is. We'll go up to the 300, maybe to 250, we'll pull out jet stream. But if you look at that low pressure system being a bare clinic low, this jet stream probably is shooting right up over that low, over the top of that center of that low. So just sucking air mass out, either causing that thing to deepen, most likely, or depending on how vertically stacked it is, or if it's stacked back to the cold air, you could judge the intensification for that thing. So if we look at the low pressure center, just off the east coast there, we got, what we do is we can go up to the 700, 500 millibar. We can pull those winds around this system and see what, give you an idea how fast that system is moving. I mean, that system's cruising pretty good, because I think that thing was over Northern Virginia earlier today, or maybe last night. I need to pull some older charts to look at that and then see the distance that thing traveled. But we can get an idea off of the 50 millibar, 500 millibar wind speeds and the 700 millibar wind speeds. See how fast that system's moving. All right, let's go to the 850. Let me run a script for some moisture. I don't want to spend too much time on these. I guess we'll just do a video on the charts. We'll just continue with the charts. We'll go up into the upper levels unless it gets boring. If it's just a west-east flow and then there's really not a lot going on, then we'll just cut it short. But then we'll do a separate video on the models, just seeing what systems are developing. We'll pull up a vorticity chart too. That'll give us an idea where any rotation is, upper level divergence. Alright, so we are on the 850. We're about around 5,000 feet. It's about 4,781 feet. Alright, that closed low system, stacking way back. I mean, we got, that thing was over Connecticut and then now it's over the Great Lakes region. I mean, it's a heck of a stack. Still are, I mean, this thing could just either shear apart or could, fill. And usually they'll start becoming vertically stacked when they start to fill, and then that's when they start to dissipate, and they'll fill from the bottom up, and you'll see that low pressure on the surface disappear first. Then the 850 it'll fill, and then that 850 will disappear. But you can always have that upper level low just up there, shortwave troughs going around the upper level low, not see anything on the surface, and falling through a cold air mass causing snow or causing rain or anything. So if that rain's above the freezing level and falling out, and it's still hitting the ground as rain, that's the cold rain process. So you can still get that precipitation from short waves moving around these lows in the upper levels. So it's always good to go to the upper level charts. I mean, even with this now, you got all that thermal advection. I mean, there's some pretty strong thermal advection with a closed low at 850. So definitely have an upper front. Look at our data, and we can see if we can find that front. And then what you can do off that front. Let me get this up here. Pull up some upper level data. I want to get this thing as thick as I can get it, because the upper level data is limited by weather stations that let go of the balloons and send that data out. So I always put this at a maximum for station plots in the upper levels. That way it's never too crowded. We'll throw one on here. Throw these station plots on here now. Alright, so if you're looking at this chart, we're looking at the thermal advection, we're looking at the wind shifts, and we're looking at the those temperatures. So we got a -14 and a 3. There's a -7. If we had to place an upper front, we could place it right through there. Right through Ohio, Kentucky, Tennessee. And basically what that's going to tell us, where that surface front is, the surface front off the East Coast, stacking back to an upper level front, then you can get an idea what the slope is. If I was to place a front over Ohio, Kentucky, Tennessee, and then had a cold front off the East Coast, then I would say, that's a real shallow slope going, from one front to the other. Now we did have that post front, that secondary front. Now you can go, if you're using that front, then you're going to go stack up to this one, and then depending on how many degrees it stacks back, we can judge it a little bit steeper slope. Now, this really doesn't do much good in the wintertime. I mean, it helps with the, some intensities, but like, you're basically looking at in the summertime when you have a frontal system come through and you start getting that severe weather, how steep is that slope of that front? Because you want to know if the leading edge of that cold air is coming through. If it's a steep slope, I mean, it's almost stacking vertically into the upper levels. It's just like a snow plow, and it's just plowing that moisture through, and then just causing real strong, fast-moving thunderstorms ahead of that front. So that's when you get the weather at and ahead of the front. You got a steep slope on that. Now, if you got a shallow slope, then you can get say your plow bucket is coming through at a slight angle, then all your weather is going to be at and behind the front. So because all your lift, when you're lifting condensation level, is to the back behind that front, so you have to hit that level because before you can become condensate, before condensation can occur, and then clouds and then convection and everything else. So that's what's going to help you if you analyze these charts into the upper levels and determine what the slope is. So we're at the 850 now. This is still considered lower levels. Looking for that upper front, and then you go up to the 700. You can see an upper front from there and get a better idea on your slope also. But you can see 30, 40 knot winds. 50, 60. Here's a 75 knot wind over the east coast where that low pressure system was. There's a 50 knot wind. So 850, pretty strong winds on the 850. But let's go up to the 700 and get a look at that. We still have significant moisture throughout the United States. So we got significant moisture at 5,000 feet over Florida, over western Texas, over the Panhandle and New Mexico. We've seen some a little bit of snowfall developing in these areas. So we definitely got the moisture to support that. So let's go up to the 700. I'm going to run a script for the moisture on that also. Alright, so still significant moisture over New Mexico, over the Four Corners, Florida, and then over the Midwest, Illinois, Indiana, Ohio. So we still have significant moisture. It's getting a little drier in the over Ohio. Wilmington, Ohio, probably right around that area. So when they let their balloon loose, we'll probably see, if we pull the Vorticity chart, we'll probably see a little bit drier air. The temperature and dew point line starting to spread apart on that Vorticity. I had them up earlier. Let's see. I need to pull up some. If we compare Vorticies from yesterday to today, we can see how those upper levels just dried out. This is, like I said, this is only 700 millibar. This is just under 10,000 feet. So now our low pressure system that was over the Great Lakes, the computer's placing the low way to the north. We have that low pressure system over the Great Lake region, but we still got some pretty strong troughing over that region. Here, let's throw the isotherms on here, and I'm suspecting they'll be more parallel with these contours. So a little bit of advection here, maybe. Not a lot. A little bit of advection right there where that moisture is. Some cold air advection going around that low. And then these isotherms start becoming more parallel with the contours. That's where, it gets a little bit more stable environment there. I mean, you can still get the moisture, still got the, precipitation, but no major precip from that. Probably just some light snow and stuff. We do have the low pressure system. Let's get some data. We'll place that low if the low is there. I mean, we have an open trough, so if we see any significant rotation, we just don't have really enough data to determine that unless we have a easterly wind. There's the rotation it's looking at, but that's off the lake, so you could have that. We do have an easterly wind there, so you definitely got some rotation there. So that's okay for that center based on the not really any data to bring that low any closer to the south to bring that stack up off the Great Lakes. I mean, that's shooting way up there, so then becoming more barotropic. So I would suspect this low's getting weaker, or is weak in the upper levels. So not a real super intense system, and plus we're losing the baroclinicity of that system too. So here's the main thing, another thing about the 700 millibar. So that low pressure system on the surface was at over Connecticut. So we got a 60 knot wind, 65, 70 knot wind, 70 knot 80 knot wind, so you're looking at 70 knot wind. 70% of the 70 knot wind be about 49 knots. Probably just over 50 knots for the 80 knot wind. So 40 to 55 knots or so. That system should be moving on the surface. That's a pretty quick moving system. That's at the 700 millibar winds. And then you can take the 50% of the 500 millibar wind, see what you got there, and then kind of average that out, and that'll give you basically your how fast that system's moving. What you're looking for too is like your winds on the right behind the fronts. So if you take those percentages of those winds behind the frontal systems, you can tell how fast that front is moving. Also, we'll pull up a couple other charts and get a good look at those fronts too, and see if they're strengthening or weakening, or see what's going on, undergoing frontogenesis or frontalysis. Let's shoot on up to the 500 millibar. It's about roughly 18,000 feet. Run some moisture. Now in Ohio we should see it starting to dry out. So pretty much drying all the way up into the Great Lakes region. So now your moisture to the north. We still have significant moisture over New Mexico. So as that moves east, we could see, a little bit more snowfall over Texas. I think we're starting to see that system develop now. What we're looking for is like that low pressure system. It's kind of some troughing moving through. I think a low pressure kind of develops around over the Gulf again, and it kind of then moves to the northeast. That's the wind. That's the weather we're going to see in the Ohio Valley, stretching all the way through Kentucky, Tennessee. We're going to see all that again. Some mixture with that cold air mass still there. See some mixture, some snowfall, and we'll look at some models maybe in the next video. See what we got. What type of precip we're expecting there, if the models are going to even be close. I mean, for Ohio, we were kind of on the line anyway, but the models had us more in the snow, and we got a heck of a lot more ice. Let's pull the height on this, and then we'll pull the isotherms. 500 millibar, still got a pretty significant trough. And then we're just getting, this is what I talk about getting boring. We're just getting, the flow from west to east. Really no advection going on. Low pressure. The low pressure is still hanging in up there. Closed low on the 500. It was showing closed on the, or showing open low on the 700, one level down. So without the data, it couldn't extrapolate that. So let me throw the data on this one. So I mean, we had that low pressure here. It was stacking out, stacking back to there. Could be just a separate upper level low. We had that low on the surface down around Connecticut, and then it stacked back to the Great Lakes region. But for one to stack back toward the colder air, jumping that far, really not likely. It may be its own upper level low. So we do have a westerly flow, easterly flow, and then a southerly flow there. So that, just the computer wants to see that rotation. Winds out of the southwest at 50 or 100 knots, 95, 100 knots. I mean, that's pretty significant. Probably looking at your jet. I mean, this would be a low-level jet, but pushing right through there for a jet max over Virginia. We'll pull the 300 and see what we got for a jet max. Right here's another area. That's 70, that's 85. Here's about 95, so you need another low-level jet right off the west coast. Still significant moisture over New Mexico, though, so any moisture, like I said, if this pushes east, we'll see more snowfall possibly in the panhandle of Texas. We'll go back to the radar, maybe look at that. And then we'll pull up a national radar. Should have already done that. Let's see. I'll do that. Place that in the center of this video. Alright, so we're going to go up to 300 millibar. Let's just run the moisture real quick, just for the fun of it. See what's still left out there. 30,000 feet. We had moisture all the way to 30,000 feet in Ohio yesterday. And then we just pretty much dried out. Right around 18,000 feet. Actually, we were only about 10,000 feet today. We shot about 10, 12,000 feet and it dried out after that. So we were still had some precip fall this morning. Frozen precip. Everything, all the temperatures in the upper levels were below freezing. If you look at the older charts, just from a couple of days, what happened with the mixture through Ohio, we got all the ice because the low pressure system at the 850 millibar level, we had significant warm air advection. We had a southeasterly wind from 5,000 feet down, and then it shifted, I think, from the southwest. But the southeasterly flow was low enough to pump the warm air into those lower levels, and then that brought our freezing level. It left the freezing level at the surface, but it brought the warm layer. It expanded that warm layer in the upper levels and made it thick enough so that the precipitation that fell through would melt, and then the freezing level, the height, thickness of the freezing level at the surface was too shallow. When it fell through, it couldn't freeze all the way back to snow, so it fell as ice pellets. So that's the reason we got mostly ice pellets. It pushed that freezing layer, further north. And we just ended up in the mixture. Alright, let's get some heights on here. We can see all of our precipitation well to the north. We still do have a little bit of precip moisture over western Texas, New Mexico area. So that is definitely that little troughing system that's running through there. I mean, you can see the troughing. Let's get rid of this. Let's get rid of these heights. I'm gonna erase this real quick. Pull up a. See if I can change that. Sometimes the computer throws some low pressure systems in there. High pressure, just it kind of doesn't get the data on it. Freaks out and it sees an upper level low, because you're gonna have, with a cold core high in the center of the United States, you got higher heights in the lower levels. So you got a little bit of ridging, and then you have troughing in the upper levels because you have lower heights, because that cold air wants to sink. So you have just your classic cold core high. Let me see what you can go to meteorology101.com, look up pressure systems, and you can probably see, the differences between when you got high pressure at the surface, you'll see the ridging, and then you'll see troughing in the upper levels, and you'll see a low above that. So then you'll get, it's a stable environment, but you'll see stuff like this on the charts when the computer can't analyze. It sees one low area of low pressure that has a open isobar, and then it has a one area lower pressure, and it just closes it off and then freaks out and throws all this through there. Now, if you were to actually analyze this, it would probably be more like this isobar sinking down a little bit further, just staying right along with these, and then the next one and the next one, and just have a trough. But you may have a upper level low, troughing in that above that high pressure system that's not this extreme. I mean, the computer's just going nuts on this thing. But we do have significant moisture to the north. Like I said, we still have significant moisture over Texas and New Mexico too. That's where that system's moving through. So that's the one to keep an eye on. We'll see what the models are doing. I'll post another video here shortly, and we'll get a good idea on that thing. Let me get rid of this chart. This thing's just making my eyes hurt. We'll go up to the 250. Let's get a better look at the system up there. Then we'll pull up the jet stream. I mean, basically, once you get this high to the 300, we're not looking for pressure systems. I mean, sometimes we are, depending on how intense those pressure systems get in the upper levels, but mostly we're looking for the jet. Let me run a moisture script on this. Probably not going to see much at all. Still over New Mexico and Arizona, there's some moisture up in that level, and then to the northeast where that low pressure system is. So we know they're going to get a bunch of precip up there. And then we got some moisture sinking down into Montana. So let's get rid of that. We'll go to look at the jet stream. The main purpose of these charts up here anyway. All right, I'll do some shading on it, and it actually shows some different colors. The hotter the colors, the faster the wind speed. So you can look at the jet max here, pushing from the northwest, and then we got that troughing right there around that high pressure system, and then right above that low, where that low was in Connecticut. So you do have that jet support. When you got jet support on those systems like that, it's like blowing air over a tube. You create a suction, and it just sucks the mass out of that low pressure system and keeps that thing alive. Let's run some pressure on this. Probably just see a bunch of troughing, ridging there, and there's a low pressure system well to the north, open low. See what we got for isotherms. We are crossing a little bit here. What's going on? We got a cold, looks like a little bit of a warm core stuff going on. Negative 48, negative 50. So a little bit warm core. Get that back down there. Nah, that's pretty open. I mean, it's trying to close off to be some little bit of warm core there, then cold core over here over that high. Just being that cold core high, you got the colder temperatures enclosed. But there's your jet max. Let's throw plots on here. See what their speeds are. 135, 140 knots, 130. So I mean, we got pretty significant jet max there. There's 135, 130. There's 150 right there. There's even stronger jet max. So we're cranking pretty good right there. And then almost looks like we're splitting here. Got some upper level divergence. So we got 150 knots, 130 knots, 130 knots going in, 150 knots coming out. So you don't have only the directional divergence, you also have a speed divergence in that area right there. Alright, so that's pretty much for the charts. Actually, no, it's not. Hold on. We are going to go to, let's go back to the 500 real quick. And then we can run I'm going to run a vorticity chart. Alright, so over the East Coast, West Virginia, we got that low pressure system was off the coast there, Connecticut. We do have positive vorticity advection around that system. This means upper level divergence, possible rotation. So we definitely got a live system there. Over here in the Four Corners area, positive vorticity, and then down over Texas, that's really some weak stuff. Let me throw the vorticity readings on here so you can get a little bit of better idea of what's going on. So anywhere these X's are, positive vorticity, and then they're going to where those cross those contours and then push into like temperature advection, which I don't see a whole lot of advection going on there. That computer's picking up a little bit stronger in that area. We're going pretty much parallel with the contours. Over here we definitely got some advection, so I would say, yeah, let's go with that to support that low. But other than that, right here, we definitely have a little bit of advection, positive vorticity advection going on right there. That's for sure. Typically, what you'll use this chart for is to look for your upward vertical motion, upper level divergence, and it can be used, to see what kind of areas would produce a little bit more severe weather, and then also, if you place the fronts on here, this is a 500 millibar chart. I'm just placing surface fronts over it, and you can say, okay, we're probably going to have that frontal system is probably going to intensify. That system's going to intensify, and then if you have a stationary front like this, but I don't think that stationary front's really there. I'd say that's going along the continental divide, so it's, that mountain range It's just riding right along that. You could have a lee side trough, some troughing or something going on there, but nothing. You know, they're just separating that mass. This computer's separating those temperatures and stuff because of the mountain range. I mean, you get into the mountains, you got a lot colder temperatures, so it's kind of like holding a stationary front there. But I don't think that's truly a stationary front. But the idea of this is if you take the positive vorticity advection and that comes superimposed over a low-level frontal zone, that's a stationary front, just exhibits a weak thermal advection, then you can actually get a low pressure system start up on that. So with this low pressure system right there, that positive vorticity advection right there over the tip of Texas, now this stationary front, some weak thermal advection, you could get a low start right in that area. So we'll look at the models in the next video and we'll see where that low pressure is actually moving to. Is this thing pushing down through here, and then I think there was some snowfall kind of over the panhandle over New Mexico, but is it pushing to the southeast, coming around that high like the last system did, kind of almost filled and then recreated over here over the Gulf and then pushed to the northeast? That's that low pressure system up there right now. Now is this one, is that doing the same thing, or do we just have another low pressure system that's going to kind of develop and then push to the northeast? Because we have our jet stream, we have our flow. Here's the flow. This is 500 millibars. We want to go, this is upper levels. We go 500. We go up to 300. With that jet stream, we see where that jet was. That's the flow in the mid levels that we're pushing. The direction of the system. So if we have a low pressure system that develops over the Gulf, then it's going to definitely move to the northeast. So. All right, couple more charts real quick, and I'm going to end this one. We're going to actually, I'm going to get over to the models. That'll be the next video. So let me get a couple more charts real quick, and we'll see what we got. All right, we're doing let's see, I don't know if I changed my height. Let's see. Yeah, I went to the surface. So this is our surface frontogenesis. Pretty much it's kind of taking those areas of upper level divergence and saying, hey, if you put a frontal system there, that's where you're going to have frontogenesis. That's where a front is going to form. So anything in the light blue, it's weak frontogenesis. You got a slight chance, and then in the darker blue, you got a pretty good chance of this system right here is going to intensify that low pressure, that frontal system, this frontal system. The stationary front, you got some there. Like I said, if that stationary front's even there, I mean, really, the low pressure system over close to the four corners, and then if you have a frontogenesis created, would intensify over New Mexico. So the only other thing I like to do with this chart is just to get some pressure on here. I'll just hit something. I don't know what I hit. Okay, it was the pressure. So there's the close. It's showing a closed low over the four corners. Probably move that low a little bit further east, but like I said, looking at the data, you have to analyze all that stuff yourself and then place that low and stuff. These charts get a little cluttered when you start adding data. Gives you an idea where the fronts are. That's all. We got, northwesterly winds, southeasterly. This one's just straight westerly. So you're looking for any rotation. Place that low. Probably bring that low over into that closed area. So I'm not spending much time on that. We were already on the surface. So I'm going to do just one more. Let's see, a couple more charts maybe. Let's see what we got, and we'll do this other advection chart. And this thing shows basically just areas of instability, and we can you can determine where any possible severe weather would be. So we got pretty intense stuff down here. If we end up with that low pressure system down there, then we can say that's a pretty good chance of development. And then off the coast, this is just chances for anywhere there's some severe weather. That stuff I moved through Florida is pretty much what's over there now. So a little bit to the north, but this is just a reference chart, just for it's more for convective severe weather stuff like that. Then we can, once we get into the severe weather season, we'll start using this chart more, and we'll start seeing where the most potential for severe weather is to develop, and then we can compare that to day to day, that tornado alley that lights up, and then we'll see how accurate this thing really is. So I think that's about it. Let me see what I could pull one more temperature chart just to show kind of where that cold air mass has just sunk way down into the south. Look at this cold air. It's like a wind chill chart. I don't know. The scripting doesn't really make sense. There's the 32-degree line, dropping all the way down to southern Texas. And then there's just your freezing air, just freezing just all through the central United States. That's your coldest stuff, where you have your strongest wind chills. So even in Texas, just based on these temperatures, if the wind blows, they're going to have a wind chill. So that's just areas of wind chill. But it just gives you an idea. Look at the air mass, just sinking down into the United States. This here's some little bit warmer air over the Great Lakes region. Like I said, we had that low pressure system pushing off. The 850 the other day was bringing warm air in the lower levels over the Ohio Valley area, and that pushed all that freezing stuff, the frozen precipitation to the north, and we had that mix of just that ice pellets, all that stuff down at around the Ohio Valley and around that 275 loop. So, all right, that's pretty much it. I want to end this video here, and I want to say thanks for watching, and stay tuned for the next video. I'm going to get through some models and see what we got there, if what we're looking for at this next storm. Thank you for watching again.